Okay, good afternoon, everyone. We're the members of Group 4, Miss Shana Simon, myself, Miss Cynthia Sommer, and Sir Javel Tom. So this afternoon, we're tasked with doing polar curves. So the objectives for this afternoon will be to define polar coordinates and polar curves. Then objective 2, identify the main parts of the polar coordinate system. Then we have convert between polar and rectangular coordinates using formulas. Then 4, we have plot points and sketch basic polar equations. 5, recognize common polar curves such as circles, cardinals, spirals, rose curves, and lemniscates. Okay, so as you can see here now, we are looking at the polar curve here. So this slide basically is talking about polar curves, which are basically shapes drawn using polar coordinates here. And instead of using the XY coordinates, polar coordinates, what we basically use, we use R. R equal theta. So this is where R shows how far it is from the center. As you can see here, we have this is an R line showing from the diagram here. This is basically our this the radius from the origin, and we know that the origin is right here, which is 0 0. So the distance from R will be somewhere here, and theta is basically the angle that you turn. So we have, as long as we have our R, we can able to form an angle for this part of the diagram here. So we need to think of it as turn an angle, and we will have the theta, which is this part here. If you move the distance, you will end up with R, which is along this part of the line here. And we can able to plot our points, which we have here. The point will be here. So it's within the form as R equal F theta, and it basically means R depends on theta. It's very important. So as theta basically changes, the distance also will change. So it's formed by plotting many polar coordinates. So they so as we can see here that it's used to create curves and shapes. So some common examples include circles, cardinals, spirals, and the rose curves. And we have an example here, which is r is equal to 2 plus 2 cos theta. So as you can see here, we have some common polar coordinates. So the first one we have here is a circle, which is r equal a. What this is basically telling us here is that r stays the same all the time for the circle in this case here. So you are always 4 units from the center. So we can say that this part of the circle here, we can see that this is 4 units here because the line would have cut directly here. So you can get a circle here. So the constant distance is basically equal to circle. Then we have the cardinal. What this is basically telling us is this is basically formed in the shape of a heart here. So this basically the R changes as the theta also changes. Sometimes it can get bigger, sometimes it can get smaller. But my colleague will be talking more about the polar coordinate, the polar curves in details. But what we just need to know is that the cardinal is basically form a heart shape. The rose curves forms is basically in the form of a rose with petals. And n petals is based if n is odd, we will have n petals. And in this diagram here, if, a rose with 4 petals. If the rose is an even number, we end up with 2n. Then we have the spiral here. This is basically an Archimedean spiral. The distance increases with the angle. So what we need to know that the key angle by varying theta and calculating r equal f of theta. So we can plot the points r theta and connect them to form smooth curves. And these are basically some of the curves that we can have when we are given a question. Okay, so we'll be looking at point in space. So as we can see here, we have the polar coordinates. So a point in space can be represented using r theta. So we can see that r measures distance from the origin. So this is our origin here, and we can measure the distance, which is r, from the origin. So our distance can be here. So as you can see, if it says that we need to find r is 5, if you go here on the x-axis, we can have 5 and we can plot our points at the top here. And by forming and by having that, we can have our angle, which is 60-degree, being formed here as well. So the theta basically measures the direction from the polar axis. So as you can see that the point is 5 and the theta is 60 degrees. So if we are going to, what we basically do here, we just move on our x-axis, we find our 5, and then we find our 60-degree as well here by just forming it here. So we basically move 5 units on the x-axis and we will be able to form our 60-degree angle here. So we have understanding radius. So this slide basically tells us here is that radius in polar coordinates. So the radius is the distance from the origin to a point. So as we can see here that this is our origin, and we can have our radius from any part here and we will form our point here. So a point to be 430. So you start basically at 4. This is supposed to be somewhere here. Let me just use annotate. So it's supposed to be somewhere here. We will have our 4, because if you look from the x-axis, we will have our 4 here. And we have our point being formed there, and from that, we'll have our 30-degree being formed here. So we need to always know that r is always a positive number, or we can say it's 0. And we can also have our next point being formed here as well, where this is 2 and, and the degree is 315 degrees, forming from here, coming there. And the radius tells us how far the point is, no matter what direction it is in. So for example, we have point A, which is 4, and the degree is 30-degree. So we can say that if we look on the x-axis here, say we have 4 here, we basically plot our points somewhere along here, and we have our theta, which is 30-degree. So our unit is basically 4 units away from the origin, and the origin is basically here at the center. So we're going to look at understanding angles. So angles are measured from the polar axis. The positive angles move counterclockwise, and the negative angles move clockwise. So the angles may be measured in degrees or in radians. So here we have a diagram showing the different angles that is being formed here. So if we look here, we can see a 90-degree being formed here. And from here to here, we can estimate that this is another 60-degree. From here to here, we can find a 60-degree here. And if we move, we can have like 120-degree here. We come here a little bit more from the origin to here, we have 150-degree. And on this line here, we have a 180-degree form. From the origin to here, we have negative 150-degree. And from around here, we should have, from the origin to here, we should have negative 120-degree. And from the origin to here, we will have negative 90-degree. And from the origin to here, we have negative 60-degree. So and then we can move from the origin to here, we can have negative 30-degree. So as you can see, as we are going in this direction here, sorry. So if we are going in this counterclockwise, we're basically going to have positive angles. If we're coming in this direction, which is clockwise, we end up with negative angles. So we need to know that the degrees is basically a commonly used unit. Like for the example that we have negative 45 degree, which is going to be somewhere around. All right, and then we have the radians, which is another unit of measurement. We can, if we don't want to use the degrees, we could basically use radians, which is pi over 4 radians. We can also use the formula as well to convert the degrees to radians. Then we have polar coordinates. It's basically used to locate a point in a plane. So it's normally written in the form of r theta. And as we know that r represents the distance from the origin. And as we know that our origin is here, and our r can be formed along this line here, and from whatever they ask you for, if they ask you for 4, we can, our r will be here, and the point that is being formed, we can get it here, and we can able to form our angle. And then we have our angle which is being formed here, which is the theta. So this will be able to show that our point is r theta. Maybe this could be like about around 45 degrees here. Yeah, sorry, this will be like 3, not 4. Sorry, my bad. So they ask you, they will tell you that the example is 345 degree, which is the wrong. Sorry about this. It's this diagram at the bottom here. So what is basically telling us here that use this. Yes, this diagram here is basically showing us where the R is from the origin. So here we have our tree, and when we take it up here, we will have our point, which you have from 3 here, and our degree that is being formed here, we have the 45 degree. So as it says that r is equal to 3, which is our distance from the origin, and the theta is basically the 45 degree, which is an angle from positive. It's a positive angle in this case here. So we have the conversion formulas here. We're looking at conversion formula where we are converting rectangular to polar. So from polar, we have r theta to rectangular, which is xy. So the formula that is given here is x equal r cos theta and y is equal r sine theta. So we are given a diagram here to show that this is our r and our point is being formed here. We come down, we have whatever is the point that is supposed to be here, maybe 3, and here could be around 45 degrees. Then from the rectangular xy to polar r theta, we have, this is the formula here, which is r squared equal x squared plus y squared. And to find the degree, we have the theta is equal tan inverse, and we have y over x. So in this case here will be the same thing where we're given the r, and when we come down is maybe the point. We're gonna have our point that is formed here, then we have our theta here. The next diagram, as you can see here, is we have the polar rectangular. So where we are converting from polar to rectangular, we have the from r theta to xy in complex form. So xy is equal r angle theta, and then it's basically equal r cos theta plus j sin theta. What is basically this j sin theta here will basically be this part here that is imaginary. Then we end up from xy to r theta. So we have r is equal to xy equal the root of x squared plus y squared. And then we have theta is equal tan inverse. Then we have y over x. And this is basically here where it's the origin to where we have our number maybe 3, and the angle that is being formed is going to put it like 45 degrees. And we basically, what we use, how to use this is that we replace cos theta with a real part. We replace sin theta with the imaginary part, which is j equal the root of -1. So how we basically use this, we find r as the magnitude, which is the root x squared plus y squared. And we find theta using tan inverse, and then we have x over y, and then we can be able to choose our quadrant here. We have an example here, which is r theta, where we are basically converting the rectangular to polar coordinates. So we are given r is equal 5 and the theta is 30. So what we do here, if you go from the origin, we can able to estimate that this is our 5 here. And if we go at the top, we will have our point here that is being formed. And we can say that we have our theta 30 degree here, right? So this is our line that we will get when we draw it from here. So if we want, we could use the formula to get our answer in this case here. So we say that x is equal r cos theta, y is equal r sin theta. So what we use the x formula first. So we have x equal 5 cos theta, and we have equal 5. If we cos 30 theta, we have root 3 over 2. So our answer will basically 5 root 3 over 2. And if we're going to find for y now, it will be y equal 5 sin 30 theta. Sorry, 5 sin 30 degree. And then we have 5 back. And when we sin 30 degree, we have half. So and when we multiply these two together, we have 5 over 2. So our answer for this part will be xy. We have 5 root 3 over 2 and 5 over 2 are the answer for being this part here. Then we have another example here, which is example B, where we are given xy and we need to put it in the form of r theta. We need to find for r and theta. So we are given xy is equal 3, 4. So x is 3 and y is 4. So what we do here now, we use the formula. R is equal to root, and then we have x squared plus y squared. So where we see x, we have to put the number 3. Where we see y, we put the number 4. So we have 3 to the second power plus 4 to the second power. So we have 9 plus 16, we have 25. When we square root that, we have the answer being 5 for this part here. So theta now, we use the formula for theta, where we have theta is equal to tan inverse y upon x. So where we see y, we have to put 4. Where we see x, we have to put 3. So when we tan inverse this, we have 53.13 degree. And this will fall in quadrant 1. So somewhere here is where our answer will be, where we have 53.13. Then we have another example here, which is example C, r theta, and we need to put it in the xy term. So what happens here, we have r is equal to 4 and theta is equal to 45 degrees. So xy, the formula we have for xy is equal r, and in bracket we have cos theta plus j sine theta. So xy, so where we see r, we have to put r 4. Where we see cos theta, we put cos 45. Where we see j sine theta, we put back our j, but our theta, we end up with sine theta 45. So when we find for cos 45, we have root 2 over 2 plus j, and sine 45 will give us root 2 upon 2. So when we would have calculated this entire thing, we have 2 root 2 plus j2 root 2. So that's the answer that we have gotten for this example here, where xy is equal to 2 root 2 plus j2 root 2. And then we have our example B here, which says xy to r theta. So we're given xy is equal to negative 3 plus j4. So we use our formula, which is r equal root x squared plus y squared. So where we see x, we have to put negative 3. Where we put cy, we have to put 4. So if you find for negative 3 to the second power, it will be 9 plus 4 to the second power, we have 16. And if you square root 25, we end up with 5. To find for our theta here, now we use our formula, which is tan inverse, and then we have y upon x. So where we see y again, we have to put 4. Where we see 3, we have to put negative. Sorry, where we see x, we have to put negative 3. So we have tan inverse y upon 3. It will be 126 degree 0.87. Sorry, 126.87 degree, and this will be for this, we will find this in quadrant 2 here. So as you can see here, from we're gonna have like our negative 3 being formed here, and our this will be where we would have gotten our angle, or angle which is being formed from here over here to here. This is where we have gotten it to be 126.87, estimated to be around here from the diagram. Then we're converting polar to rectangular. So we need to convert 445 to rectangular coordinates. So again, we have our formula here, which is x is equal to r cos theta. Then we have y, which is equal to r sine theta. So what we can basically do here, we need to start from the origin to plot our points here. We stop at 4. And then when we go up, we can have our xy here. And start from here to here, we end up with our 45 here. So this part here will be our r is equal to 4. All right, so when we're gonna put this in, so now we need to find for x. So we use our form, which is r cos theta. So where we see r, we have to put 4. Where we see cos, we put the 45 So we put back our 4 here, and cos 45 will give us root 2 over 2. When we solve for this part, we have 2 root 2, or we can, when we convert, we can have 2.83. We need to find for r, sorry, we need to find for our y now. So y is equal to r sine theta. So r will be 4, sine theta will be sine 45 So when we sine 45 we have root 2 upon 2. When we multiply by 4, we have 2 root 2, or we end up with 2.83 here again. So the rectangular coordinates that we have is x will be 2.83 and y will also be 2.83. So we're going to convert in rectangular to polar again. So we have to convert 3, 4 to polar form. So what we basically do here now, we we start from origin. This basically from this part here. So we need to move 3 units to our right. So if you move, this will be 1, this will be 2, and this will be 3 here. And we need to move 4 units up. And as you can see that it will be somewhere here, right? But our angle will be formed from the origin to this point here. So that is how we will end up with a 3, 4 here from this diagram. So if you're going to use our formula to find for 3, 4 in the polar form, the formula here that we use is r equal root, and we have x squared plus y squared. So where we see x, we need to substitute that with 3. Where we see y, we substitute that with 4 here in our formula. So we have 3 to the second power, which would be 9. 4 to the second power would be 16 here. So 9 plus 16 is root 25. And when we root 25, we have r will be equal to 5 in this case here. So they're going to say that our r is from here, which is going to give us like 5. Sorry for this. Yes, so this is where we would estimate this to be our 5 here. So now we need to find for our angle. To find for our angle now, we use the formula, which is theta equals tan inverse, and we have y upon x. So we have back our tan inverse. Where we see y, we put back 4. Where we see x, we put back 3. So the tan inverse of 4 upon 3, we end up with theta equal 53.1 degrees. So now we are looking at the rectangular coordinate system. So it's a way to locate points in a plane using two perpendicular number lines called x-axis and the y-axis. So the x-axis, as we know, is goes to the left. Sorry, it goes to the right here. My bad. Yes. If the x-axis, as you know it, it's on our right, going to our left here. And as you know, our y-axis will be from top to bottom. All right, so these lines basically cross at the center, and this is our origin, as we have talked about this earlier. And the point, as you can see here, as you can see that it consists of two perpendicular number lines, right? The axis, the x-axis, which is the horizontal left to right, or a y-axis, which is vertical going up to down. And then, as you can see that we have this part here. From here, we can say that, sorry, not this. So as we can see, they would say that the axis, they intersect at the origin, which is 0, 0. So as we can see that we have a uh, perpendicular line here. Sorry about this. And here, so it's perpendicular, right? So the origin is basically the reference point for all the locations. The xy we have here, any point is located using an order pair, which is xy. So you move along the x-axis to x, then you move up or down along the y-axis to y. So we always write our coordinates as xy. So the example, the points shown are located at order pairs. So we have 3, 2, we have negative 2, 3, then we have negative 1, negative 3. And if you have 3, 2, this day, 3 is basically our x value or x coordinate. Our 2 is basically our y coordinate. And the same goes for your negative 2 is our x, positive 3, y, negative 1 will be x. And the negative 3 here will be our y coordinate. So as you can see on the Cartesian plane here, we have, or for the xy coordinate, we have 3, 2. So we look at our x, if I locate our 3 on x, and and on our y, we locate our 2. That is how we have this point being formed here. Then we have negative 2, 3. We come on our x-axis, we locate negative 2 here. And on our y-axis, we locate our positive 3. That is how we have this next point here on the diagram. And the same goes for negative 1, negative 3. We come here. We located our negative 1 here. And we move to 3 points down. So this is how we end up with our next point here. So this is how we get our 3 points on this Cartesian plane here. We have 1 and this 2 here, and this one will be 3. Now my next colleague will be taking you through this slide.
Okay, so now we would look at plotting points in the coordinate, polar coordinates. So I would just take you through as it relates to radians and degrees. So you can basically calculate the angles in degrees and in radians. So this example, uh, our R value, which is, let me annotate, our R value, which is 3, and our angle here, which is pi divided by 4, pi over 4. And in degrees, that would be 45 degrees. So basically from the origin to A, we have a point that is in blue here. So our R value, which would be 3, and we have our angle there. So point A, we have 3 units at 45 degrees or at pi over 4. Next slide. All right, so now I will walk you through some other examples. So it says find the polar coordinate equation corresponding to we have uh, x squared plus 2y squared equals 6. So we need to utilize our formula. So we're going to substitute for x, we'll replace that with r cos theta. And y, we're going to replace that with r sine theta. Um, so now we're going to use our equation and we replace x with r cos theta and we bring down back our square. So we square that. Bring down our 2, replace y with r sine theta. We square that and we equal that to 6. Um, Now what we do, we just square both terms. So r square cos square theta plus we simply multiply 2 times r sine theta and square that. So we have 2r square sine square theta, and that is equal to 6. So now what we're going to do, since we have r square in common, we're going to factorize that. So we take that outside, and we're left with cos square theta plus um, 2 sine 2 sine square theta equal to 6. So that is how we find the polar coordinate equation. Yes, so now we look at another example. So this one is um, transform the equation. So we have an equation here where r is equal to 8 cos theta to a rectangular coordinate equation. So we're going to use this formula here. So r is going to be equal to um, root x squared plus y squared. And our cos theta, that is going to be equal to um, x divided by r. So now we're going to do some substitution. So we have r, where we see r. We're going to write root x squared plus y squared. So we replace r with this value. Equal, we have 8. And where we have cos, we're going to substitute um, our x divided by r. So x divided by r, well, we replace r with root x squared plus y squared. And basically this root x squared plus y squared, it's dividing. So when we take this over the equal sign, and we take that over the equal sign, the two root signs, basically that will cancel. So we'll just have x squared plus um, y squared. Example would be like root 2 times root 2. So that would basically give you 2. So that's the same thing that we're doing there. So that leaves us with um, x squared plus y squared is equal to 8x. And to write in the equation form, um, it's already an equation. So we just need to take over the 8x, and when we take that off, it becomes a negative 8x. So x squared minus 8x plus um, y squared is equal to 0. And that is how you work it. That's how you transform it to a rectangular coordinate equation. Now we will move on to another example, some other examples. So next slide, please. So now we're going to perform a polar equation to rectangular form, transforming a polar equation to rectangular form. So example, r is equal to 5 divided by 2 sine theta minus cos theta. And the steps are followed. So we start with our equation right here to rewrite the equation, and then we perform our multiplication. Um, so basically what we do, uh, we have 2 sine theta minus cos theta, so that is dividing. So we take that over with r. So since it's dividing, it goes over and multiply. So now we have here, which is r times 2 sine theta minus cos theta equal to 5. Now we substitute the coordinate. We're going to substitute. We're going to use cos theta. We're going to use x divided by r. Sine theta, we are going to use y divided by r. So we just replace those. So in this case, we have r times, in bracket 2, times y divided by r minus x divided by r, close bracket, equal 5. And we basically would have to simplify. So we simplify by distributing r. When we distribute r by what is in the bracket, that will give us 2y, and r times negative x divided by r. That will just give us x because the r's will cancel out. So we have our equation written here in the rectangular form. Yes, so now we will look at another example, transform the following equation to polar coordinate equation. So we have 3 of them. The first one, we have y is equal to 4. So what we do, we substitute. So we're going to use this formula here, where y is equal to r sine theta. So we have r sine theta is equal to 4. And what we can do next is we take sine theta over the equal sign to leave r by itself. So we have r is equal to 4 divided by sine theta. And if we were to take sine up with a 4, so it's going to be the reciprocal of sine, which would be cosec, or yeah, cosecant. So we have r is equal to 4 cosecant theta there, and that would have completed it. Now moving on to b, we have 3x minus y is equal to 0. So in this case, we're going to use x is equal to r cos theta, and y is equal to r sine theta. So we just substitute our x and y values, or x and y. So 3 times r cos theta minus, well, we have y here, so replace that with r sine theta. Minus r sine theta is equal to 0. Then we factor out what we have in common. So in common, you can see we have r's in common, and we write back this in the bracket, which is 3 cos theta minus sine theta is equal to 0. And we divide by r cos theta. And when we do so, that will give us sine theta divided by cos theta equal 3. And we know sine theta divided by cos theta will give us tan theta, which is equal to 3. So that's how you reduce it further or break it down further. Now moving on to C, we have x squared is equal to 4y. So substitute, replace x with r cos theta, replace y with r sine theta, and we work it out. So where we see x, we substitute, but we replace x with square, and we have 4 times r cos theta. So we work this out, square r, and you also square cos theta. We multiply, or we distribute, r times 4 times r sine theta. And next we divide by r cos theta. Divide by r cos theta, which r is going to equal to 4 sine theta divided by cos theta, cos squared theta. So we have r is equal to 4 tan theta sec theta. Moving on. Yeah, so now we're going to look at the types of polar curves. So we have the circle, and that is a round shape. We have the rose, there will have petals. It's basically like a flower. Um, card cardioid, which is the heart shape, and we have the limison. So you'll have like a loop or dimple, and you have the lemniscate, where you have the infinity sign, and the spiral um, winding outward. So we have the signs to signify the shape of each. Moving on. Yeah, so with this example, we're looking at a circle, and the circle we have R is equal to A. So all points are the same distance from the origin. Points are the same from the origin, and the graph forms a perfect circle. And example, R is equal to 3. So our R value is 3. And remember, it's R is equal to A. So since R is equal to 3, we know that A is also equal to 3. So it means the distance here, which is A, is 3. So from this distance here, we know that point A, which will be 3, 0, 3. If you go up, that would be Y would be 3, 0, 3, because it's on the line. And if you go to the left, negative. So our A would be -3, and 0, -8, so -3. So you can check and you will see the distance apart are all equal. So the distance is r. So that makes it a perfect circle. Moving on, the next slide, please. Yes, so we have a polar cardioid graph, and we have the formula there, which is r equal 1 plus, sorry, not the formula, we have an equation, rather. R is equal to 1 plus cos theta. So the explanation, let's go through that for us. We have our equation, as mentioned before. The shape, well, it's going to look like a heart-like curve, and R varies as theta changes from 0 to 2 pi. So R will vary. So basically, when you're drawing the cardioid, you will have, in some cases, most cases, you will have A plus B, and when you add those values, that will give you the distance here. So that will give you the distance. So R is equal to 2, theta is equal to 0. So we do not have an angle there. Theta is at 0. And yeah, basically you can see it here. R is equal to 2. So when you add your A and B, it should give you that 2. So when you come down here, let's say you come down here, it will give you negative A, and you go up. Well, we can see this is a positive A, and this positive A would equal to 1 across. You add it 2, A and your B, A plus B, and that will give you your 2. So the distance here is going to be twice what's going up here. Sorry about that. Moving on to the next slide. So here we're going to focus on the rose curves. The equation we have here, R is equal to A sine n theta, or R is equal to A cos n theta. So where A is a constant and n is a positive integer. So we're going to focus, firstly, n is a odd number. So when it's an odd number, we have n petals, meaning odd petals. So example, R is equal to A sine 3 theta. So basically you will find the number is 3 because it's odd. We have the exact number of petals, which is 3. So when you draw it, it will look just like this diagram that is shown here. So you can count. This is 1, 2, 3, 3 petals there. That's an angle. And moving on to R is equal to A cos 5 theta. So we have the same amount of petals here. So 1, 2, 3, 4, 5. Equal distance apart from each other. And here, there's a note that says, when n is odd, the rose curve has exactly n petals. Yeah. Now moving on to even. So if n is even, 2 times n. So it will be 2 times the number of petals. So in this case, we have the number which is 4. We know 4 is even, so 2 times 4 is 8. So we have 8 petals in this case. Here we have 6 even, times that by 2, we have 12, so we have 12 petals. So when n is even, the rose curve has 2 times n petals. Symmetry. Let's look at symmetry. Rose curves are highly symmetrical about the pole, meaning the origin. The initial line, which is theta equal to 0. The line theta is equal to pi divided by 2, and the other lines through the origin. So they're symmetrical. Moving on to the next slide, please.
Yes. So moving on, we're continuing with the rose curve. We have the polar rose curve. The formula that we're looking at is R is equal to cos 4 theta. And when K is equal to 4, which is an even number, it creates 8 petals, as we can see in the graph below there in red. Now, for the polar coordinates, we have the example when it comes to plotting the points. So in our bracket, we have 2 and theta over 4. The 2 would be what we call the radius, or it tells us how many points we're moving. And the theta over 4 tells us our degrees. So we would be moving in the positive direction to 2 and moving up at an angle of 45 degrees. The second point that we're going to plot, we have -3, and our angle is 2 theta over 3, which is the same as 120 degrees. So our arrow or point would end up on the negative side of our x-axis. Next slide. Now, there are different types of spiral curves in polar coordinates. We have the first one, Archimedean spiral. The second one, the logarithmic spiral. The third, the Fermat spiral. And the fourth, the hyperbolic spiral. And with the first one, Archimedean spiral, R is equal to theta. The logarithmic spiral, we have R is equal e to a power. The forward spiral, we have R is equal to the positive and negative roots of theta. And the hyperbolic spiral, we have R is equal to 1 upon alpha. Next slide. Now, we use the graphing calculator Desmos to give us an example or as to how these curves would look. So the curve that we mentioned before, R, or the equation, R is equal to the cos of, we could have 4 theta, in this case we have k theta. What is it our graph would look like when k is equal to +1? And that is what we have here. Our radius being, or diameter in this case being +1. Next. Again, we use Desmos to prove the different equations. R is equal to theta, which gives you the Archimedean spiral. Next. Now next we have the lemniscate, and that equation is r squared is equal to a to the it's a squared cos 2 theta. And with this graph here, it looks somewhat like an infinity sign or 8 that is to the side. It has two loops and it is symmetric about both axes. Next slide. So we have the various shapes of the lemmaton, how these can be formed. Now, before we look at the different shapes, we work with the equation r is equal to a plus b cos theta. Now, this curve changes its shape based on the values of a and the values of b. It can have 1, a smooth curve, 2, a dimple, 3, a loop. And a lemmaton is a type of polar curve related to the choroid. Now let's look at the different shapes of limacons. We have the first one when the A value is more than the B value. We have no loop, no dimple. It looks similar to a circle. The dimple now, when the A value is equal to the B value, we have that slight dimple on one side of our curve. The loop, when the A value is larger than B value, we have something similar. We can say with a sideways 8 where one side is smaller than the other. We have the coordinate where A is equal to B. That shape similar. You can say to a heart. And we have the exact circle where the B value is equal to 0. And as we mentioned before, the lemniscate where A is equal to 0, it gives you a perfect 8 or infinity sign. Next slide. So we have this example here as it relates to plotting a point. It shows the point 3 with a degree of 45. So we are moving 3 on the y-axis and we're moving at an angle of 45 degrees. So we move 3 units from the origin along that line and we move 45 degrees. Now this simple example here proves that the radius r, which is 3, and the angle or theta in this case would be 45 degrees. The next example. So this example with the parotid curve, we have the equation that was given earlier. R is equal to 2 plus 2 cos theta. And they are asking us to sketch that, and it mentions 3 points there. The graph forms a toroid. It is symmetric about the x-axis, and the maximum radius occurs at theta equal to 0 degrees. So the toroid curve now, or that shape, it has a heart shape. That is how we're able to recognize what type of curve it is. So we have there r is equal to 2 plus 2 cos theta. And we have 2 minus 2, which gives us 0. That is on the y-axis, it's 0. And then they gave us the maximum radius at theta equals 0 degrees. R is equal to 2 plus 2 cos 0 degrees. which gives us 2 plus 2, which is 4. That is how we have the point 2, 0. Next, so we have to convert 5 and 30 degrees to rectangular coordinates. To convert these, we use formulas. So we are given our radius, we are given our angle, our radius being 5, our angle being 30. And we use the formulas y equal r cos theta, x equal r cos theta, and y equal r sin theta. We substitute our values. 5 cos theta is the same as 5 times the root of 3 over 2, which gives us 4.33. Y equal 5 sine 30 is equal to 5 times half, which is the same as 2.5. And by using those simple formulas or equations, that is, and simple substitution, that is how we convert our point into rectangular coordinates. Next slide. So we have to convert 6, or radius 6, and angle negative 45 degrees, the rectangular coordinates here again. They give us formulas, or their formulas that we're working with, the same set of formulas. So we substitute our values. We have the first equation being x equal r cos theta, r being 6 theta. Pardon me, sir?
No, it's my phone went off. That's all.
Yes, theta being negative 45 degrees. So we do simple substitution, and our first value, x, is approximately 4.24. Same thing, we work with our y. Y is equal to r sine theta. We substitute our values, and y is equal to negative 4.24. So now we have our rectangular coordinates being our x and y values, the x being 4.24 and y being negative 4.24. And that is how we are able to plot our points on our graph. Next. So we have to convert 4, 3 into polar coordinates. We have our points, our x and y, and we have to use the formula r is equal to the root of x squared plus y squared. We know x is 4, y is 3. Simple substitution, and we have r is equal to 5. Now in this case here, they didn't give us our degree, they didn't give us our angle, so we have to find it. So theta is equal to tan inverse y upon x. We know y value, we know our x value. Simple substitution, so we know our angle now is 36.9. So therefore, 4, 3 in polar coordinates is 36.9 degrees. They gave us our radius and our degrees we just found. Next. Now we have to sketch the graph. R is equal to 4 sine 2 theta. This equation was mentioned before. So that 4 now, each petal has the length of 4. That determines how many petals are going to be on our graph. So we have our First petal there at 90 degrees, where R is equal to 4. Our second petal at exactly 0 degrees, where R is equal to 0. Third petal, theta is equal to 270 degrees and R is equal to 0. And our fourth petal, theta is equal to 180 and R is equal to 0. So because of that 4 sine square theta, that's how we know that, okay, our curve or our graph in this case would have the 4 petals, a maximum of 4 petals. Next. Now that brings us to the end of our presentation, and we have 3 points to conclude. The first one being, polar curves provide another way to represent and graph mathematical relationships. Second point, they help to describe circular and symmetrical patterns more effectively than rectangular coordinates. The meaning of this is that they give us a radius and they give you an angle, so you know specifically how to plot your point. Third point, through coordinate conversion, plotting and graph sketching, we can better understand the behavior of different curves. Thank you. That's the end of our presentation. Any questions?
All right. Yeah. Uh, anything you all want to ask and so on? One thing with this class, I'm going to end the recording before we. How do I stop recording?